Now, this problem continues. We just looked at finding your upper and lower bounds. Let's go ahead and find the m for your M&M theorem from this one here. Remember, it says take your largest coefficient or constant up here, which would be your negative 8, over your leading coefficient. So you take your negative 8 and the absolute value over your 2 and absolute value, and you add 1. So you get 4 over 2, or 8 over 2, which is 4, plus 1, so you get 5. So that means all your zeros should then be between negative 5 and positive 5. Well, the more precise way to get your zeros where they are located is your upper and lower bounds. Well, we had a lower bound of negative 1. We had an upper bound of 3. Are they within our 5 to negative 5? Yes, it is. So the upper and lower bounds are more precise but take more work. The M&M is less precise but quick and easy. So let's go ahead and do Descartes' rule of signs on this problem. Remember, to find your positive roots, you got to count the sign changes. Your positive to a negative, that's a sign change. Your negative to positive, so that's a sign change. Your positive to negative, that's a sign change. So for your positive roots, you have 3 of them, or it could be 1 of them, because remember, it's equal to the number of sign changes, or you go down by increments of 2. So we got to find our negative ones. So we put in a negative x for each one of these. Negative x all cubed times 2, negative 5 times a negative x squared, a 4 times a negative x, and a negative 8. Then you got to simplify. Remember, a negative to an odd power changes your sign. Negative to an even power does not change your sign. And so then you count your sign changes. Negative to negative to negative. No sign changes yet to negative. Oh, no sign changes at all. So you have no sign changes. So your 3 here could be paired up with the 0, or your 1 here could be paired up with the 0. Now, since our degree is 3, you know when you add across, it has to add up to 3, so that means in this top situation, there would be no complex. Here, when you add across, you would know there'd have to be 2 complex. And in this case, that's your chart. There's nothing left. So then go ahead and graph it to see if all your zeros occur between. And you will notice on your graphing calculator when you type this into your y equals and graph it, it crosses between here and here, and it always ends up being between these two when you cross the x-axis with your graph. So, suppose we want to go ahead and use Descartes' rule of signs here. And you were just told from working out a problem that you had 3 positive roots and you had 4 negative roots with a degree of 7. So that means you could still have 3 or 1 for your possibilities for your positive. But negative could be 4, or remember you can go down by increments of 2, so it could be a 2 or it could be down to a 0. So when you're looking at this, your 3 could be paired up with the 4, or your 3 could be paired up with the 2, or your 3 could be paired up with the 0. 3 can't be paired up with anything else, so your 1 could be paired up with the 4, or your 1 could be paired up with the 2, or your 1 could be paired up with a 0. Now remember, your number of roots is always equal to your degree. So when you add across here in any of these rows going across, it always has to add up to your degree of 7. So the first situation, there wouldn't be any. But here, you'd have to have a 2. Here, when you add across, this would have to be a 4. Here, when you add across, it would have to be 2. Here, when you add across, it'd have to be 4. Or at the bottom one, when you add across, it'd have to be 6. We need to take this function and write it as a product of linear factors. That means inside the parentheses when it's factored, the highest power you want inside the parentheses is 1. They are being nice to us though, and they're telling us that 4 is a 0 and that it shows up twice because it says multiplicity of 2. So we're going to use our synthetic division, put down our coefficients and constants from up here in your original problem. Remember, you're missing an x to the first, so you're going to have a 0 as a placeholder. And we're going to go ahead and plug in 4. We know 4 should give us out a 0. If it doesn't give us that 0, that means we messed up since they're telling us it works. So you bring down your 1, multiply that red 1 times your 4, you add down, you multiply, you add down, you take your 2 times your 4, you add down, you take your 4 times your 8, you add down, and it does give us our 0. Since 4 works, we know that x minus 4 is a 0, or a factor. So then what we have here in red then is your quotient. So if I write that, it would be a 1x cubed, a negative 5x squared, a 2x, and an 8. Now, we know that 4 works again. So 4 should go into our quotient again. 4 went into your original, and we have that. But 4 is supposed to work again because it says multiplicity of 2. So now all we're going to do is just work with our quotient. And we're going to do synthetic again. So we bring down our 1, multiply, add down, multiply, add down, multiply, add down, and it works a second time. So that means, and we knew it should work, but we had to verify it, that means your x minus 4 works twice. So it's really an x minus 4, an additional x minus 4, but an x minus 4 times an x minus 4 is an x minus 4 all squared. Well, we really then also need to have our quotient of what's left over. That would be what we have here in green. That would be a 1x squared minus an x minus a 2. Now, we want it written as a product of linear factors, so we don't want to leave it as a quadratic here in green, so you want to factor that even farther yet. Are there any factors of a negative 2 that add together to give you that negative 1 right here? And well, yes, we could use an x minus 2 and an x plus 1. What we have here is it being written as a product of linear factors. Now, if you did need to go ahead and find your zeros, we have it written as a product of linear factors, but if you did need to find your zeros, to extend this a little bit more, what would cause this parenthesis to be 0? A negative 1. What would cause the middle parenthesis to be 0? A 2. Now, they're both to the first power, so you know they're both simple multiplicities or multiplicities of 1. When we are looking at this one right here, you would have a 0 of 4. But since you have an exponent of 2 on it, you would know it would be a multiplicity of 2. Which means, graphically speaking, it would bounce off your graph rather than your x-axis rather than actually crossing it. These two here would actually go ahead and cross it.